Hello, everyone. My name is Shadeep, and I'm your instructor for today's course. And I'll help you prepare for your FE exam today. And the topic that we are going to talk about today is solid state electronics. I'm pretty sure a lot of you guys have already taken that course if you are in the junior level or at the senior level. So, first, what we'll do is how I progress is usually I start off giving a basic idea what the topic encompasses, go choose what content you exactly need for your FE exam, and then eventually we'll solve some relevant questions based on that. So how about we start with the basics right now? So a lot of you, okay, so let me just show you the content first, and then I'll just walk you through what you exactly need to know about this. So let me start sharing my screen. Okay, so uh, not this one, not this one. Yes, yeah. So it's actually this one. So in solid state electronics, we will basically learn about semiconductor materials. As you could see from the name itself, we'll focus on the semiconductor materials. We will talk about electrons and hole mobility. That is one of the things that we will be focusing on. We would try to focus on the built-in potential, the thermal voltage. I'll talk a little bit about this, about the capacitance of like when it comes to solid state electronics. We'll talk about amplifiers. We would focus mostly on BJTs. Uh, then we'll talk about a little bit about diodes, Zener diode. We would also talk about a little bit about BJTs. Again, like this is when it comes to this is small signal analysis, which is basically AC analysis. We would also focus on large signal analysis, which is DC analysis. So we would go through that. We would also focus on JFETs and MOSFETs. We would focus on the N-channel JFET, the P-channel JFET. We will focus on the three regions in which they are operating: cut-off, triode, saturation region. There's a small signal analysis. We would also focus on that. Just giving an overview of what topics are there, and then we'll just go step by step so that you know exactly what is expected out of you in the exam. And this is basically the enhanced spin MOSFET, more or less the same equations. So yeah, that is basically what solid state electronics is. And these are basically the equations that you would be needing on it. Also, you'll need some op-amps as well. So basically what you would be needing is the gain for an inverting amplifier and a non-inverting amplifier, the concept of common mode rejection ratio is there. Yeah, so these are the only things that you need for solid state electronics. But before I start, we would just go through some very basic overview, and then we'll move on to the equations. Now, the thing is, what is expected out of you is you understand nowadays that almost everything, every chip is made up of a semiconductor, right? And the semiconductor that is most likely used is silicon, right? So silicon is something that we mostly use. Now, the thing is, now silicon is a semiconductor. There's a difference, right? There are three types. Uh, Let me just show you with a diagram. Start with a new page. Just zoom it in. So let me just start. Okay. So basically, there are three types of substances. One is definitely the conductor. Then there's the insulator. We have all we already know what a conductor and insulator is. And from the name itself, we know a conductor is something that allows you to conduct electricity, right? A conductor is something that allows you to conduct electricity. Similarly, an insulator is a substance that does not conduct electricity. So a conductor is a substance that conducts electricity, and an insulator is a substance that does not conduct electricity. Okay, so a semiconductor falls somewhere between a conductor and insulator. So that's why it's called semiconductor. I think I'm making sense somewhat. So when we study about solid state electronics, we are usually focusing on semiconductors. Okay. Now, the thing is, how do these things actually conduct electricity? And how can we change? So a conductor helps you to conduct electricity. An insulator does not conduct electricity, but you can change the property of a semiconductor and increase its conductivity by doping. Doping is a way that helps you to increase the conductivity of a semiconductor. Now, there could be two types of doping. One is p-type, and the other is n-type. Okay. So two types of doping. One is p-type, and the other is n-type. Now, if you're wondering like how a p-type semiconductor works, let's look into some of the equation. So over here, the conductivity of a semiconductor, let's look into this equation. So let's go through what exactly you need to know. So if they ask you to figure out what is the conductivity, because semiconductors are basically used to conduct electricity, like they don't have as good, they have to, the property falls somewhere between conductor and insulator. So when it comes to semiconductor, if they ask you to figure out how much is the conductivity, you would basically use this equation, where N, as you could see, is the electron concentration, P is the hole concentration. So N is for electrons, P is for holes. This one is the mobility of electrons, because N is for electrons, so mobility of electrons, multiply the mobility of electron with the concentration of electron, and the mobility of the holes with the concentration of the holes, and you just add them up. Okay, so we are assuming the semiconductor has both N-type and both P-type. If there was no P-type, you would just ignore that, and you would just focus on the N-type. But supposedly there is both an N-type and a P-type, which is usually the case when it comes to MOSFETs and all. So you have to, you just add up the concentrations and the mobility. Okay, so the electron mobility with the concentration of electrons and the hole mobility with the concentration of holes, just add them up and you multiply with the charge of a single electron. The charge of a single electron is 1.6 into 10 to the power minus 19. So once you multiply all this with the summation of the concentration of electrons and the concentration of holes, you would get how much is the conductivity of that particular semiconductor. Okay. Now, if it's a p-type material, they're definitely saying that this is how you can write the concentration. And if it's an N-type, this is how you can represent it. So A as an acceptor. Okay, so P-type is called acceptor. D as in donor. I'm not sure whether you are already familiar with these terms, but in case you are not, so P-type is related with acceptor and N is related with donor. Okay, so at equilibrium, assuming that it is at equilibrium, the concentration is nothing but equivalent. So P and N are equal, so you can write intrinsic, I as an intrinsic. So the intrinsic semiconductor concentration square equals to that of, yeah, it's written over here, intrinsic concentration of semiconductor is the concentration of holes multiplied with the concentration of electrons. Any confusion with this? I hope not. Okay, so and the next thing that you need to know is there would be a potential difference. Okay, so there would be at the p-n junctions. Suppose you have a P and an N. So this is supposedly the P, which is equivalent to acceptor, and N is the donor. So between the barrier between the holes and the electrons, there would be a potential built-in voltage. And they might ask you to calculate this voltage. So I'll explain to you in detail, but if you're trying to calculate it, if you're trying to put a number to it, it is nothing but the concentration of, so the intrinsic concentration square, which is this, it is divided by actually the concentration of acceptor, the concentration of donor. Okay, you take a ln of this one. So the ln of concentration of acceptor, concentration of donor, and divided by the intrinsic concentration square. You multiply it with a constant value, which is this. Now, K is actually a Boltzmann constant. Okay, it would be given to you how much value it is. It's given to you. So actually, as you could see over here, it's given to you as 1.38 into 10 to the power minus 23 joule per kilogram. Okay, so that's the Boltzmann concentration. Okay, and then if you're wondering how much is the Na is the concentration of acceptor, D is the concentration of the donor. Okay, so once you multiply that and divide it by this, and you take a ln, and this is the Boltzmann constant, T is the temperature. Okay, so usually we can assume the temperature is like 300 Kelvin or 298 Kelvin, whatever it is, and you divide it by the charge, which is actually 1.6 into 10 to the power minus 19. Charge is 1.6 into 10 to the power minus 19 Boltzmann constant. T, this is a constant value. You can just figure it out. And you just have to, so basically the concentration of the acceptor, the concentration of the donor, and the intrinsic semiconductor concentration, which is more or less actually fixed, but is actually going to affect how much is the built-in voltage. Now, when it comes to diodes, we usually say that built-in voltage is 0.7 volt. Okay, for diodes, the built-in voltage is actually 0.7 volts. And that is the reason you need to apply at least a 0.7 volt for the diode to actually conduct. So if you're applying less than 0.7 volts, it does not conduct. Okay, so you need to apply at least a 0.7 volt for a diode to conduct electricity. So just to recap what we talked about so far, we talked about three things. These are the three equations. Okay, so let me just take another snipping tool so that now let's move on to the next two equations, and then we'll recap what we just talked about. So we talked about three equations so far. Let's just start with a new one. Okay, now coming over to this next set of questions. Now, if you're trying to figure out how much is the capacitance, okay, so your next question would be, okay, I know that there's a P and an N junction, and I could pretty much figure out how much is the potential. And I need to at least apply this potential for it to conduct electricity, for the electrons to actually flow through this. Okay, so this is the barrier voltage that I need to overcome. The next question would be, so obviously, there is also a capacitance between the PN junctions. So it's not just a voltage, there's also a capacitance between those. And how exactly are we supposed to calculate that capacitance? So C naught is the junction capacitance as zero. Now, this capacitance would obviously vary depending on how much voltage you're applying to it. Okay, so the amount of voltage you're applying to it is actually going to affect the capacitance. Okay, so if you're trying to figure out how much capacitance you need to apply, C naught is a junction capacitance at 0 volt. That means when you are not applying any voltage to it. Okay, provided you're not applying any voltage to it, if you're trying to figure out how much is the capacitance, this is what you need to do. The next thing is the potential at the anode with respect, then you apply a voltage. Okay, so that is what you need to figure out. Okay, this one is the potential of the anode with respect to the cathode. This is the potential that you're basically, in a subtle way of saying the potential that you apply. So this is the capacitance when no voltage is applied. This is the capacitance when you're applying a voltage to it. And BI is junction contact potential. Okay, so this voltage would be actually given to you. Okay, so BI is nothing but a junction contact potential. So far we studied one equation, we studied the second equation, we studied the third, and we studied this fourth equation. Okay, now moving on to the next equation. If you're trying to figure out the resistance, okay, now let's move on to the next. So now you're basically trying to figure out how much is the resistance of this one. So the resistance is actually given by this equation. Okay, so the sheet resistance, this RS is actually the sheet resistance, which is nothing but the resistivity divided by the thickness. So the thickness of this one, how thick it is, it's also going to affect eventually its resistance, because we already know R equals. So if you remember, like for resistance, we usually use this equation, R equals to rho L by A. Okay, so obviously it's not exactly the same, but you can say more or less it's the same. Okay, so if you're trying to figure out the resistance of the diffuse layer, it is nothing but the sheet resistance, which includes the resistivity and the thickness of the diffused layer, the length of the diffusion, which is L, and the width of the diffusion. So the length of the diffusion and the width of the diffusion, when you take the ratio and you multiply with the sheet resistance, and the sheet resistance is actually derived from the resistivity and the thickness, you can basically figure out the resistance of the diffusing layer. Okay, so these are a couple of equations just to recap what we just did. And this is basically the solid state electronic equations that you need to do. We'll solve some relevant questions, but just let me minimize it. Just a small recap. And then we'll solve some questions based on this one. So for what we recapped was we tried to figure out how much is the conductivity of a semiconductor. So again, so we were saying that there are three types, right? One is the conductor, one is the insulator. Conductor allows you to conduct electricity. Insulator does not allow you to conduct electricity. Semiconductor is somewhere between an insulator and a conductor. Good for you. Now, once you understand the concept, the next question is conductivity. You're trying to figure out how much is the conductivity of the semiconductor. As I said, the reason why we dope it is to increase the conductivity. So obviously now you could see that the conductivity is basically increased depending on the concentration of the electrons and the concentration of the holes. And when you multiply it with the mobility, you can basically figure out the conductivity. The next equation that we tried to focus on was the carrier concentration. So how do I find out the carrier concentration? As in the intrinsic concentration, it is nothing but a square. It's square of, it's the product of the electron concentration and the hole concentration. That was the second equation. The third equation we focused on was the built-in voltage. How much voltage is there between this P and N? That is figured out by this constant, which is Boltzmann constant given. T is the temperature, Q is the charge, ln of the concentration of acceptor, concentration of donor, and intrinsic. We forgot one thing. The thermal voltage is a fixed value. All you have to know is just, you have to just remember that Vt is always fixed at 0.026. It's a fixed constant. Okay, so you just use this value. Whenever you see Vt, you just use the value as it is. Okay. The next thing we try to figure out how much is the capacitance. So the capacitance was C naught. That means the capacitance when you are not applying a voltage, but when you're applying a voltage, you're trying to figure out that voltage. So this will be the voltage that you're applying. And VI is the junction contact potential, which would be given to you. And yeah, that's the equation as you would use it. The next thing that you would focus on is the resistance of the diffuse layer, which includes the resistivity sheet resistance, which is nothing but the resistivity divided by thickness. And then you basically take the ratio of the length and the width, and you can basically figure out this whole thing. I hope you kind of understood what the concept is. So I'll stop sharing my screen. Right now, what we will try to do is we'll try to solve some relevant questions just to make sure that you actually understood the concept. Okay. Okay, so how about we start with a couple of questions? So let me just. So this is a question that's given to you. And so what they're saying that the intrinsic carrier, now see the intrinsic concentration is given to you. Ni is 2 into 10 to the power 10. Okay. And they told you the electron and the hole mobility is at, mobilities are given to you of the electron and of the hole. So they're just asking you to figure out the conductivity. I'm pretty sure I gave you this equation. So as usual, I'll give you around 5 minutes for now. I'm just going to zoom in a little bit for you. Okay, I think you could see the question now. I'll give you like 5 minutes now. First equation, obviously, as I said, where the conductivity is nothing but the charge, concentration of electron, hole, mobility. Okay, so you have to know that it was given like this. This was the second equation where, remember, it's given like, okay. So obviously over here, they're assuming since, okay, it was given to you, the mobility of the electron, the mobility of the hole was given, the charge was given. Okay, and so since this is this, so obviously this is N, this is P, this is the, and the charge was 1.6 into minus 9. If you multiplied it, you would have gotten this question answer. I hope it did make sense to you. It's just that two equations, first and the second equation, you just have to use those two concepts in order to solve this. Okay, so how about I give you another question? Okay, let me stop sharing my screen. Okay, just let me just give you another question. Okay. Start sharing my screen. So this is the second question. Let me just zoom in. I think you can see it. Let me zoom in again. So now they're saying the concentration of acceptor is this. And the concentration of donor is this. And the intrinsic concentration is this. So they're asking you to calculate the contact potential. I gave you the equation already, so you just have to use that to solve it. Okay, so how about I give you 5 minutes now? So let me just go through the solution. Okay, so what they did, let me just zoom it in. This is the equation that you would be using, and it was already given to you as we discussed in the reference handbook. The Boltzmann constant, Kt by Q, this thing is always constant as it was given to you. So always, this is actually Vt. Okay, this is represented by Vt. Okay, remember I was talking about it. So this is 0.026, and A was given, and D was given, and Ni was also given. So all you had to do was plug in, and you see it's 0.634, which is almost equal to the potential of a PN junction of a diode. So you need to apply that at least a 0.7 volt for it to start conducting, right? So this is what they were saying, that you need to apply at least a 0.63 volt for it to conduct. Okay, so yeah, so I think like I basically recap what we need to know. We tried to go through all the equations that you need. We need a couple of equations. We kind of solve all the questions, relevant questions based on it, so that you are now a little confident how to do it. I'm still here. If you have any questions, just reach out. But yeah, so we'll stay here until like